Okay, exam 2, number 1C. So let's say we do use a coordinate system with the x-axis that way, the y-axis that way, and that means the z-axis has to come out towards us. Then in the y direction, the starting thickness of y in the y direction is 1 centimeter. And we calculated already that the deformation in the z direction, the strain, is negative 1.85 times 10 to the minus fifth. And we also calculated that Poisson's ratio is negative EYY over EXX, and it's also equal to negative EZZ over EXX. And this is equal to 0.274. And so that tells us that EZZ, no, YY is what we want now, is equal to negative 1.85 times 10 to the minus 5 also. And so EYY is equal to the deformed length in the y direction minus 0.01 divided by 0.01. And this is equal to negative 1.85 times 10 to the minus 5. And so then that says that negative 1.85 times 10 to the minus 7, if I multiply both sides by 0.01, is equal to Ly minus 0.01. And so Ly is 0.01 minus 1.85 times 10 to the minus 5. And that's meters. So we're better about putting units on answers this time, but there still were a few people who weren't doing it. I still didn't take off any points for not putting units on, but that day is coming. So. Yes. Right. And you can figure all that out by thinking about what the compliance matrix does. Well, if you know the units of one of them, then you can figure that out. Like if you remember that strain is unitless, for example, and you know that stress is pascals, then you can figure out that Poisson's Young's modulus has to be also pascals. Any other questions about the test? Okay. So let's go back to internal loads. Internal loads in beams. So let's do a problem where we have a cantilever beam connected to a wall on the right. and a distributed load applied like this. The maximum value of the distributed load is 10,000 newtons per meter. And let's say the length is 2 meters. And we want to know what are the internal loads. And this time we're going to calculate them as a function of x. So the point on the left is, we're going to call that x equals 0. The point on the right is x equals 2. Let's also put a torque on here. So let's say that we're also going to torque this end with a magnitude of 700 Newton meters. Okay, so x equals 0 is on this side, and 2 is on this side. So it's just telling you where along. Okay, so we're going to do a cut where this time, normally the first thing we would do is calculate the external loads, the reaction loads at the wall. We don't have to do that this time, because when we make our cut, we're going to take a piece that starts on this side and ends somewhere in here. And so those reaction loads at the wall don't even come into it. So we can skip that first step. And then now I'm just going to take an arbitrary piece of this that starts over here and ends somewhere over here. And we're going to call this end, the distance from all the way at the left to this, we're just going to call it x. And x has to be somewhere between 0 and 2. So a free body diagram, and this is going to be valid for any x between 0 and 2. So we're going to include some amount of the beam, and then we're going to skip some amount of the beam. I'm going to draw this over here just so we remember, so you can see what we're dealing with and what we're not. And over here, there's going to be at the wall, that's a fixed joint, so there's going to be some kind of reaction force, and there's going to be some kind of couple. And then the distributed load is going to so there's all this part of the distributed load, including the part that gets up to a maximum of 10,000, but that's not included in our free body. And then there's this distributed load. There's the couple of 700. And then there's the tension, the shear force, and the bending moment. And then the torque. We want to calculate all of those internal loads. Yeah, plain T, fancy T, M, and V. And the dimension says that this is equal to x. Okay. Well, before we can do this calculation, we have to represent that distributed load as a point force. And so we have to think about this distributed load as a shape it has a base of x. We don't know what that x is, so we just have to leave it like that. And in order to come up with the area and the centroids and all this stuff, well, I guess we can come up with the horizontal centroid position just from the x. But we do have to know the magnitude of that force, right? We know that the centroid is going to be a third of the way, so this distance is going to be 2x over 3. This distance is going to be x over 3. Okay, so that we know, but we don't know the magnitude of the force that that's going to apply yet. And to do that, we need the area of this triangle. And to calculate the area of that triangle, we have to know what the height is on the right side of the triangle. We know that for the whole triangle, the height is 10,000, but obviously this, it's an arbitrary distance, so it can take any value between 0 and 10,000. So what we need is to represent the height of this triangle as a function of x. Okay, so anybody have an idea how to do that? So similar triangles. Yes, that's a good way to think of. So I was going to think about it as using the function, of a line. That's what we're doing, is just representing this line as a function. But you can come up with that same function by doing it as similar triangles. You know that 10,000 over 2 is equal to h over x. And so then it works the same way. I tend to think of it as the function for a line. So this is equal to mx plus b. When x is equal to 0, what's the height of the triangle? Or what's the height of that line? Well, yeah, so we're trying to figure out what m and b are now. So if this is a function, this function represents a line, and this is x equals 0, what's the value of that, the y value of that line when x is equal to 0? 0. And so that b goes away. And now how are we going to find the slope of that line? And just do rise over run when x is equal to 2. So that's going to be, so the rise is 10,000, the run is 2. Times x. So this line is 5,000x. And now that we know that, we can redraw this free body diagram. So there's all this stuff going on, but that doesn't come into our calculation. And then there's a downward force applied by the distributed load with a value of 5,000x. That's what we just calculated as the, oh, no, we didn't. I'm getting ahead of myself. Sorry. We're not done with this yet. So this is the height of that triangle. Now we have to calculate the area of the triangle. Okay, so what's the area of a triangle with a base of x and a height of 5,000x? So the area is equal to 5,000x times x divided by 2, so 2,500x. So that's the value of this downward force, 2,500x squared. And then we have the torque, 700. And then we have the tension, shear force, bending moment, and torque. And now that we've represented that distributed load as a point force, now we can finally do the math. So first, let's add up the forces. So Newton's second law says, does that 700 apply any forces? This is supposed to be a couple. This is a torque. It's twisting like this, and with two equal and opposite forces. Well, I did the worst thing you can do. I used my left hand for the right hand roll. But that way, so it's twisting this way. So that doesn't produce a force. The only forces are this, and the shear force, and the tension. So we have 0, negative 2,500 x squared, plus T0, plus 0, negative V. That negative V is because you can think of this vector V as a magnitude V times a unit vector in the downward direction. So, V times 0, negative 1 gives you 0, negative V. And it's static, so those are equal to 0. And that tells us that the tension is 0. So there's no tension or compression on this beam. The shear force is negative 2,500 x squared. It's algebra from here, so just add negative V to both sides, add positive V to both sides. Yep, it comes out negative. And now the moment equation. And I would recommend, you don't have to, you can use your about point wherever you want, but I would recommend just always do it at the same place. And a lot of things will come up in every problem, and you can sort of see when things are going right and when they're going wrong. So this is our about point. So now what's going to produce moments about the, well, let me do the moments about the x-axis first. Just keep it in the same order. So now we're only dealing with couples with an axis of rotation of x. So is that 700 going to produce a moment about x? Yes. And that arrow is in the positive x direction, so this is positive 700. 2,500 x squared? No, the coordinate system I'm using has x like this. Z coming out towards us. So positive 700, and then the only other thing that produces a moment around the x-axis is fancy. So 700 plus the torque is equal to 0. And so the torque is negative 700. And now we'll do the moment about the z-axis. So this is x. Now we'll do Rn2L about the z-axis. And this red dot is the about point. The 700 doesn't produce a moment about z. The 2,500 x squared does. And so the way to think about that, for the people who took statics with me, if you wanted to write it out with a row vector and a force vector and a moment and use the cross product and stuff, that works fine. But these are always horizontal, so it's a little slower to do it that way than just to do it the way I'm going to do it here. So we're going to imagine this is the hinge. we're going to say there's this downward force with this magnitude, and that downward force would make it rotate this way around the hinge. Okay, that's clockwise, so we know this moment is going to be negative. And what's the moment arm? 2x over 3. Okay, so 2x over 3 times 2500x squared. And then we said that all of that together, taking all those directions into account, we knew the moment was going to be negative. So that's the moment from the distributed load. The next thing that'll produce a moment about Z is that shear force V. So what's the moment arm for V? X. So we have a moment arm of X, of force magnitude of V, and would that make it rotate clockwise or counterclockwise around the about point? Clockwise, so that's also negative. And then we have a couple, the bending moment, and nothing else produces moments about the Z-axis. That tension, its line of action goes right through the about point, so that doesn't. And so all this is equal to 0. Yes. For the M. Right, because those are couples. And I'll show you something after this. Okay, so this comes out to be 5,000 over 3 is probably 1666, right? So negative 1666.6 repeating x cubed minus Vx plus m is equal to 0. Rearrange, and m is equal to Vx plus 1666.6 repeating x cubed. Well, we've already calculated what V is. So substitute negative 2500x squared in for V. And it's this times x plus 1666 repeating x cubed. And so you get m is equal to negative 833.3 repeating x cubed.
So if we wanted to go about the exponent, wouldn't that just get rid of the x term and just change our distance from the 2x over 3 to x over 3 and change our sign?
You would have, so if you made your about point x, you made this your about point, there would be, the moments then would be, okay, so you would still have all the same forces. All right, so you still get the same forces because this would look exactly the same. And then when you went to rotational Newton's second law, the moments that you would have would be the couple and the 2500x squared with a new moment arm that, I guess that would be x over 3, and it would be positive. Yeah. And presumably, well, let's think about what it, because this one is actually easy to calculate. That moment arm would be x over 3, and so 2500 x squared times x over 3 is 833 x cubed. And so 833 x cubed plus m is equal to 0, and you get the same answer. I would recommend just always doing it from the left because well, for one thing, it just means that every calculation you do looks the same, you know? So you're always going to have a v term that's equal to negative vx. I can't really think right now if there are any bigger reasons than that. You will get the right answer, though, that's for sure, because you totally can choose your about point. But I remember feeling like at some point I decided that it seemed you're a lot less likely to make mistakes if you always did it from the same direction with the same about point. Okay, so we got these, and now what we say is that any x value for any x in the range from 0 to 2, if you plug in the value of x you're interested in, it'll tell you what the internal loads are. You can plot these functions. I'm not going to do that right now. The easiest way to do that is with Excel or what's the Desmos, yeah. But so if you graph them out, you can sort of get a sense of where you're most worried about the beam breaking. So let's look at these individual ones and figure out where are these maximum for the different internal loads, and is there one place where like does every place, like every one of these internal loads, is it biggest in absolute value at a different spot, or is there one place where everything looks especially bad? Internal tension, there's none anywhere, so that doesn't help with anything. Negative 2500x squared, that's going to be biggest in absolute value at the wall. So the closer you get to the wall, the bigger the shear force is. The torsion is the same the whole way, and then the bending moment is also going to be biggest at the wall. So because of the shear force and the bending moment telling the same story while everything else is constant and they don't tell any story at all, we know that the beam is more likely to break as you get closer to the wall. And that means that if you use the values of those internal loads at the wall to calculate stresses, those are the stresses that you want to compare to your like limits to see whether this thing is going to be able to withstand this or not. Yes. To to graph it. Yes. Yeah. Desmos. And that's just, I don't think I've ever used it, but people, I know everybody seems to use it now. That's just free online software, right? And then if you have Excel, like you can do it with Excel pretty easily too.
So when we're talking about those like material limits,
Mm-hmm.
does that come from one of our stress tensors?
Yeah, so we're gonna figure out how to get stress tensors for this over the next couple months, you know, and different materials break in different ways, but so there's not like one simple way to figure out whether all, you know, one simple test for any kind of material to figure out if it's going to break. But if you have a really brittle material, it's probably just going to break due to the maximum shear stress getting too big. And so then you can just like look it up in a table or Google it or something, like for concrete, you know, what's the maximum shear stress that it can withstand, and then you just compare then you find your shear stress, you find your stress tensor, take the principal stresses, use those to get the maximum shear stress and compare that to this online value. And if they're close, then you're, or if your calculation says it exceeds that limit, then you want to fix something in your design. Yes. Okay. Yes. Yes, that's right. Anyone remember what the relationships are between V and M and the distributed load? So let's let, so here are the main checks that we're going to use. So if V of X is the shear stress, not the shear stress, sorry, the shear force. M of X is the bending moment. Q of X is the distributed load function. And this has to be downward for this to work. So this is the one when we found that mx plus b equation, the equation for that line. That's our distributed load function. And the relationship is dm dx has to be equal to v. And dv dx has to be equal to negative q. Okay, so let's make sure that that holds for this problem. dm dx, 3 times 833.3 repeating is, so you get negative 2500x squared, and that is that shear force function. So that one works. And then dv dx is negative 5000x. Take the negative of that, and you get, where is it? This, the function that represents the height of that line at a given x value. So for our example, this one and this one both work. It gives you a little more confidence in your calculations. There, it doesn't, it's not a guarantee that you got it right. There are places you can make mistakes that'll carry all the way through, and those will still work, but it can catch some mistakes. It doesn't, it fixes, it makes some parts quicker and some parts longer, and in the end, it's a good way to think about it. The problem is you have to match up boundary conditions, because what you'd be doing is you calculate that shear force V, then you have to integrate that, but now you have constants of integration. And the way you fix those is by saying, okay, well, the bending moment here has to be equal to the bending moment, or the shear force here has to be equal to the shear force here. Is that right? No, bending moment. Anyways, boundary conditions. And by the time you're done with all those boundary conditions, you haven't really saved any time. But you should try that sometime if you're interested in, just want to see what it's like. You can do it that way. Yes. Mm-hmm. 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 Yep. Yeah. Yeah. How do you know?
Yeah, like I saw it in the solution where the material was given the Calmax stress.
So you're given a stress tensor with maximum shear, and can I see the problem?
Found the stress
Number what? Oh, well, so in any kind of truss, all you have is tension along one axis, right? Or compression or tension. And so that means that the stress tensor you get is a principal stress tensor. And that means that the maximum shear stress is going to be rotated 45 degrees from the middle, the axis corresponding to the middle eigenvalue. So it's just, that's true in any kind of tension or compression thing for any member that's in pure tension or compression and it's brittle, so it's going to fail in shear. That failure pattern is going to be rotated 45 degrees off. Yeah, you have to do it about the middle one. So if there's two repeated ones, like in this case, you can do either of the two that are 0. Okay, let me do something, and we'll talk about it after class. Okay. Um. Okay. So, what is it about couples? What's cool about couples? Um, they don't depend at all on the about point. That is not true of anything else. The moments produced by a force in general changes if you change the about point. So the moment produced by a couple doesn't depend on the about point. Okay. So let's see why that is. It's a pretty short, simple proof. So let's say that this is the object, and let's call this point P1 and this point P2. And I'm going to say this is the about point. For now, we're going to see that that doesn't come into the calculation in the end. And let's say that the forces, so the definition of a couple is that you have equal and opposite forces. So let's call this force F and this also has a magnitude of F, but it's in the opposite direction. Okay. And I'm going to call this one, the one at the place I'm calling P1, I'm going to call that the vector S. And that means that the other one I'm going to call negative F. Okay. So what I'm going to do is calculate the total moment produced by this, which means calculating the moment produced by F and then calculating the moment produced by negative F and adding those two together. And what we're going to see is that when I add together the moments produced by those two, the appearance of A in this calculation is gonna disappear. And what that'll say is you could move that A anywhere you want and you'd get the same value. Okay. What? Nope. Actually, it doesn't depend on that. You could project it off into, yeah, that's right. Um, okay, so the moment produced by F is so the moment is row vector times F. The row vector here would be from A to P1. So that would be P1 minus A, the coordinates of those two things, crossed with F. Okay. And the moment produced by the other one would be quantity P2 minus A crossed with that force is negative F. And now you can distribute that through. You can do that with a cross product. So you get P1 cross F minus A cross F plus P2 crossed with negative F minus A crossed with negative F. And then you can rewrite these as minus P2 crossed with F. And this one is plus A cross F. These two, I guess I'll just carry down here. They're still, I guess. You see what you get is um, a minus A cross F and a plus A cross F. And so those two cancel. And that's the only place that A appears in that moment. And so that tells you that it doesn't matter where you put A. And so you can rearrange this and it comes out to the quantity P1 minus P2 crossed with F. No dependence on the about point. No dependence on the location of A. And so that's why when you have couples, if like in the case where you're adding up the moments about the x-axis, if everything is a couple, you don't even have to bother to choose an about point because those couples produce the same moments no matter where you would choose it. Any other questions? Okay. Yeah. This would be just like any kind of object. That doesn't have to be a beam. This is just talking about couples in general, you know, and you use couples in dynamics and V-form and everything, statics. But this is why you treat them a little differently than you treat the moment produced by a single force. Okay, what I'm going to do, I'll put it on D2L. I'm not planning to give you really an assignment over the break, but I am going to have you do one of those short outlines. Just so skim over your notes, do one of those short outlines, remind yourself what we've covered so far, and then we'll get back into it after. When I say one page, I don't really, I mean, I just mean not 10 pages and not one sentence. Yeah, right.